This lecture will continue talking about UART, talk about more of the bits that are transmitted in addition to the data bits and the start bit. So parity bit, this is an optional bit that you can transmit with the data. So transmission is assumed to be error prone. This is very common in long distance communications. You can have lots of electromagnetic radiation, some kind of noise, right? So this may be synchronization accuracy or inaccuracy or something like that. There are lots of reasons why there can be noise on the line. So there can be times where you expect a zero is being transmitted, but the receiver receives a 1 instead, or vice versa. You transmit a 1, but the receiver receives a 0 because of various types of noise. So to adjust for that, to take care of that, at least to detect that, we have parity bits. So a parity bit is optional. One parity bit can be sent with each packet, each, say, group of 8 data bits. The parity bit is used to check for errors. So the parity of a sequence of bits, so let's say we're sending 8 bits, 8 data bits. The parity is the count. You either have even parity or odd parity, and it's related to the number of ones that are transmitted. So if you're transmitting 8 bits and an odd number of those ones, an odd number of those bits are ones, then you say you have odd parity. And if an even number of those bits is a 1, then you have even parity. So parity is always going to be even or odd. Let's say even is 0 and odd's 1. So parity of any sequence of bits is always even or odd, depending on how many bits you're transmitting. So what we do is, if we use a parity bit, we send the data bits, and then we also send one more bit, which is the parity bit, which is either 0 or 1. A 0 if the parity of the other bits is even, a 1 if it's odd. And then what can happen is, on the receiving end, it can check the parity. So it can count the number of ones that it received, and checks if it's even or odd, and then it compares that to the parity bit. If the parity bit is even, if the parity bit's 0, let's say, indicating this even parity, and it has an even number of ones, then it assumes, okay, transmission was fine. Where if it gets odd parity, then it assumes that transmission was not fine, and it needs a new transmission. It basically sends us some kind of request to say, send me the data again. So as an example, and this parity bit is sent after the data bits. So you start with you have the start bit, then you have the data bits, then you send the parity bit, then you send the stop bit or bits. You can send one or more stop. So here's an example. We've got some series of bits, 8 bits, and there are 5 ones in those 8 bits. So it's an odd number of ones. That means this set of 8 bits is odd parity. So the parity bit that would be sent with this would be a 1. So you send these 8 bits, then you send one more 1. And the total parity is odd. So now at the receiving end, as it counted the number of ones that came in, it counted 5 ones. It realized that was odd, compares it to the parity bit. And if the parity is also 1, the parity bit's 1, then it says this is OK. Where if one of these bits was flipped in transmission, then the parity would have changed. Say a 0 was changed to a 1, or a 1 changed to a 0. Either way, the parity would have become even, and it would have noticed a mismatch. So if a single bit is changed, then this can be detected using a parity bit. Now note that this is sort of a minimal check, because if 2 bits are altered, then you won't detect it, right? Because 2 bits, say you change a 0 to a 1, then you change a 1 to a 0, then the total number of 1 stays the same, even though the data is still incorrect. So you wouldn't catch that. If 2 bits are changed, you might miss it. But you would miss it if 2 bits are changed. But if a single bit is changed, you could detect that using the parity bit. So in addition to the parity bit, you have to have stop bits. Now the parity bit is optional. Stop bit is required. Although you can have 1 or 2 stop bits, you have to have at least 1 stop bit. So in this example, this timing diagram, we show 1 start bit at the beginning, 8 data bits, no parity bit, but then we have the stop bit right at the end. Single stop bit in this case. Now the stop bit, basically it's high. It's always high. So after the 8 data bits are sent, and a parity bit, if the parity bit is going to be sent, the signal should be high. So the stop bit is the time when the signal is high after the transmission is done. It's expected to be high. You can send 1 stop bit or 2 stop bits. If it's not a high, if it's not a 1 at that point, then it's assumed that an error has occurred and retransmission is going to be required. So data throughput versus baud. So the baud rate is the maximum number of transitions in a second, the maximum rate of transitions, which is the maximum bits that you can send. And it's true, you can send that many bits, but not all of those bits are actually data bits. So the data throughput is not as high as the baud rate, because you're sending the stop bit, the start bit and the parity bit. Stop bit could be 2 bits, and the parity bit. You're sending this extra stuff that is not actually data. So the data transmission rate is going to be less than the baud rate. So these signaling bits have to be sent. So let's imagine an example where you're sending 8 data bits, you're sending 1 parity bit, and 1 stop bit and start bit, let's say. So you're sending 8 data bits, but there are 11 actual bits that you have to send in order to send the 8, right? Because you got to send the start bit, the parity bit, and the stop bit. Now let's say the baud rate is 9600 baud. So 9600 baud would be the maximum rate of number of bits, 9600 bits per second can be sent. But you're sending 11 bits to send 8 data bits. So your data throughput would be less because your transmission efficiency is only 8 out of 11. So you get 73% efficiency out of that. So your data throughput rate is actually only 73% of 9600. So you get 6981 bits per second of data that you can actually send when you're using 9600 baud under those assumptions. Thank you.